Hi students, in this final video for online lecture 13, we are now going to talk about pi bonding and our various bonding modes. So now in our last video with our hybrid orbitals, you saw the importance of orbital overlap. In this case, we need to now see how they do overlap. This is called the bonding mode. This is the orientation of how the hybrid orbitals will interact with each other, and it can be done in one of two ways, either end to end or side by side. Over the next few slides, you're going to see us go through the examples of ethane, ethylene, and acetylene to explain this. So let us go ahead and look at the molecular geometry of ethane. Our carbon-carbon bond is going to be formed by the end-to-end overlap of our hybrid orbitals. That can be seen right here in this bond of our two hybrid orbitals. If this end-to-end overlap occurs, we are going to call that a sigma bond. It has its highest electron density located on the axis of the bond directly between the two atoms. The other sp3 orbitals from our carbon are going to form sigma bonds with the 1s orbitals of our hydrogens, and you can see that is how we would get our tetrahedral molecular geometry for both of our carbons. Where the difference comes in for our ethylene is that our carbon-carbon bond is going to be slightly different. The carbon-carbon bond still contains the sigma bond, in which we see it right here, in which we get the end-to-end overlap, but we are going to have an electron in each one of our p orbitals that have been unhybridized, and these are going to want to participate in the structure of our ethylene. How this does this is it forms a pi bond. A pi bond is formed by the overlap of two regions above and below the plane of a molecule. So what you will see is that these two unhybridized p orbitals above and below can now interact by orbital overlap. These are going to be weaker interactions because they are not directly between the axis of the two atoms, but it is going to allow us to have more electron density as we are going to create our molecule. So for a pi bond, we are going to have those electrons now populated above and below the plane, and this is going to give us increased stability in our molecule. Double bonds include one sigma bond. We see that in our figure A, and that bond is located directly between the two atoms. And it does include one pi bond. So this is how we get the shorter and stronger bond than we saw than just a single bond, but this is where our Lewis structure lets us down. If we look here at figure E, we are just going to draw two lines in between our two carbons. But this does not explain the inequivalency of our two types of bonds. One of those lines is going to be our sigma bond, and one of those lines is going to be our pi bond. This is another shortcoming of the Lewis structure being oversimplified. So when you see a double bond, you know that one of those bonds is going to be a sigma bond, keeping our atoms together in an end-to-end manner, and then we are going to add the electron density of our pi bond to help shorten that bond and increase the stability. So finally, if we go to acetylene, you can see here that we are going to have a triple bond, but now, based off of our figure, you are going to see that we have our sigma bond located right here, directly between the two, and now we are going to form two pi interactions. One of those pi interactions is going to be with this black colored orbital above and below. You can see that here, as well as the black orbitals hidden at the bottom. And then our second pi interaction is going to be created using these maroon orbitals. Now, instead of being just above and below, they are out to the sides. So as we are going to have more pi electrons, we would have two pi electrons in our black pi orbital. We would also have two pi electrons in our maroon orbital. So when you see our triple bond in our Lewis structure, this is going to be one sigma bond with two pi bonds. So the lines of our Lewis structure are an oversimplification, just telling us the number of electrons, but it doesn't tell us the orientation of those electrons. For our sigma, they are right between the atoms, causing the strength of the bond, while the pi electrons are going to be above and below, or outside to the left and to the right, and are just adding to our stability. We've seen this when dealing with our bond enthalpies. Normally, the single bonds are weaker than that of the double and the triple, but it is not a mathematical addition of them, and that is because when we get to our double and triple bonds, we are adding that electron density, but it is not in between the two atoms, so the strengths are not considered equivalent. So one of the important things that needs to be discussed is the fundamental problem about our ideas of our binding modes and our orbitals. So let's look at C2H4. I've drawn two structures that can be predicted for C2H4, one with the atoms all in a plane, and the other in which the CH2 group has been rotated 90 degrees. We now need to figure out which one is going to be best. So as you can see here, we have our double bonds in here. Remember that our double bonds are created by p orbitals. So I can draw a p orbital in above and below in the case of my left carbon, and I would also have it above and below for our right carbon. Notice that we are going to get a nice interaction between these two orbitals because they are in the correct phase and correct orientation. If I go ahead and look at my right figure, you are going to see that I would have this going up and down. But now, because that second CH2 group has been rotated 90 degrees, I would have to rotate my available pi bonder 90 degrees. Notice that these are not in a good phase. This does not interact on that. They must be linear when it comes to this. So when dealing with this problem, we would fully expect the left representation to be the correct representation. So as you can see here, figure A is the correct structure because as they are both sp2 hybridized and we have the correct orbitals drawn in above and below, so now we are able to interact correctly. So when dealing with our hybridization, we also now must look and see if our unhybridized orbitals that are going to participate in our pi bonding are also in the correct phase that they need. The reason why this is important is that we are now going to restrict bond rotation. You are free to rotate around a sigma bond. This means that you can turn the various sides of a molecule. However, once you have formed a pi bond, the orbital overlap will be disturbed if we end up breaking it. If we were to try and rotate this attachment here, we would interrupt and break our pi orbitals that you see at the top and the bottom. Molecules don't want to do this. So once you form a double bond, we are going to get what is called bond restriction, meaning you can't rotate. So if you have just a single bond, you are free to rotate that molecule as you see fit because the end-to-end overlap is not going to be disturbed. Once we form our pi bond, it is stuck in the way that it is going to be bound. So if this happens, you will now see that we get two different types of molecules. For our top one, our chlorines are both coming out at us, and they are on the same side of the molecule. This would be named as cis. If you see the CIS nomenclature, this means that they are on the same side of the molecule. Well, if we were to go and break that interaction, rotate like we said, and now you can see that the chlorines are on opposite side, this one being back, while this one coming out at us, we are now going to call that trans. Trans meaning that they are on opposite sides. So how can we easily draw this? Well, for our top one, we can go and have our H Going to our carbon, here's our double bond. So now you are going to see the cis isomer here. Notice that we are going to get the isomer. Isomer meaning that the attachments to each atom are the same, but they are in a different three-dimensional space. So then for our second one, we would end up having an H with a carbon double bond, but now this chlorine is on the same side as that H. This chlorine is here. And finally, we would get our H here. And notice that they are different. These are called isomers. These are different from another type of change. If I were to go and have both chlorines on the same carbon, notice that I have changed the attachments. This is called a constitutional isomer. A constitutional isomer means that I have changed the attachment locations. This being two chlorines on this carbon and two hydrogens on here. So these are different molecules and are considered constitutional isomers. These two species are either called stereoisomers or we just call isomers because they have different three-dimensional geometry. It is important that you know the difference between these two molecules. For the final thing we're going to do in this video, let us take a look at example 7.10 and try and figure out how many pi bonds and sigma bonds we have located in our molecule. For this example, we're going to use one of our 4 nucleic bases, and this is going to be adenine. Using the structure of adenine, how many sigma bonds and how many pi bonds are located in this structure? The first thing and easiest way of doing this is looking for our pi bonds. Remember, pi bonds are located in our multiple bonds. So for that, I have 1, 2, 3, and 4 pi bonds. You can see them all marked by a check mark. So that means that I can get rid of answer A, answer D, and answer E. What now becomes more difficult is finding all the sigma bonds. One, because we have what is partly condensed structure, and we have to go back and count certain things. So I will make sure to number these appropriately. Notice that I have used a shorthand notation for some of these attachments. So while I have this carbon attached to a hydrogen, there's still a bond there. So what we're going to do is sometimes not draw the bond in, but it is inferred that it is going to be there. So let us start at our amine group here at the top. This is going to have a nitrogen with 2 hydrogen attachments. So this is already going to have 2 sigma bonds. Sigma bond number 3 is going to be located here. If we want to then go in a counterclockwise manner, we would have 4, 5. Remember that this one right here is going to be number 6. Here is 7, 8, number 9, and 10 will fill in the ring. We now have number 11. This is number 12. Number 13 attaches the hydrogen. We have number 14. 15 attaches this hydrogen. And finally, we have number 16 there. It is best when you get a problem such as this to go out and write as you're going through all of the bonds. So as we see in this example, our answer B is going to be correct, in which we have 16 sigma bonds in our entire molecule and 4 pi bonds. In this video, you saw how the binding mode can be oversimplified in our Lewis structure, but now it is able to help us understand not only our bond stability, but also the different bonds that you are going to see in many molecules, including your biochemistry and organic chemistry in future courses. Have a great day.